Hi everyone. Today I'm going to be talking about semantic quality assurance for industrial maintenance procedures. I'm Caitlin Woods and I'm representing the University of Western Australia along with my contributors for this project. So this project forms part of my PhD thesis and we'll get into how this work falls into the scope of a larger project as I progress through this presentation. So today's talk, I'm first going to go through the context of the ontology, how and why it was built in the first place. And then I'm going to give an introduction to the ontology for maintenance procedure documentation that we created as part of this project. The short name for this ontology is OMPD. I'm then going to go through how we use this ontology in a semantic quality assurance use case, and a workflow that we created to perform this quality assurance titled Quokka. And finally, I'm going to finish with what this presentation and what this work means for the industrial data ontology community. So industrial maintenance is the activities performed by organisations to keep their heavy equipment, such as pumps, trucks, etc., operating as planned. And this is a huge operation for many organisations, with some organisations spending up to 60% of their operational expenditure on maintenance. And for a very large company, this can amount to millions or billions of dollars every year. So there's many parts to industrial maintenance, from identifying work, scheduling work, executing work, and then analysing that work again so that maintenance strategies can be improved over time. Specifically for this work, we look at maintenance procedure documentation. Maintenance procedure documents are the documents taken by technicians when they go and perform maintenance work, taken with them to their job location. In many organisations, and this was the case when we started this work back in 2019, and it remains the case today, these documents are still paper-based, existing in PDF formats that have been designed by different engineers over an extended period of time. Over time, these PDF templates change. So in this slide, we can see that this document contains, for example, job hazards, the tools and materials required for the procedure, and some steps and maybe some images for how to perform the work. So a technician will grab this document, take it with them to the work location to perhaps fix a pump or repair a pump, and then annotate this document as they work, take it back to the office space, scan this document and upload it back to a computerized maintenance management system. And at this point, much of the valuable data about the work that was performed gets lost. So being designed by different engineers over different periods of time using different PDF templates, we have a situation where some maintenance procedure documents have different formats, have different styles, or look a bit different to one another. So for example, this procedure document is a inspection document. So it's a preventative maintenance task. We want to prevent equipment from failing in the first place. So this document describes how to go out and check the equipment. If the equipment is beyond some limit, for example, if the oil level in a truck is too low, then some actions or corrective actions would be required to fix that issue before it becomes a real problem for the organisation. So this just goes to show how different procedures can look different and contain different types of information. So as I mentioned earlier, this work falls into a larger body of work. So my PhD thesis was called Digital Transformation of Industrial Maintenance Procedures. When we started this work, there was lots of rhetoric around giving technicians tablet devices or head-mounted displays to work with procedures. So we went into an organization with these grand ideas about how we were going to create interfaces that, say, adapted to a technician's domain expertise or the complex environment that technicians work in. But what we found was that at that time, because we started this work in 2019, that's not really what organizations were requiring. From a technician's perspective, what they really wanted was someone to sit down and listen to them about the issues and concerns they have about using digital devices in their work. And for the people who use the data on the other end, the maintenance engineers and the maintenance planners, they were still concerned about data being in a PDF format, not being able to query across the data or really understand what was in it. So we separated this thesis into two parts. In the first part, we sat down, listened to technicians, and fed those ideas into how we can design good interfaces that work well for technicians. But of course, if we're creating a digital interface, we need a generic model to understand the concepts in a maintenance procedure, be able to query across it, and be able to check it for quality at scale. And for this, we create an ontology for maintenance procedure documentation. So now I'm going to introduce OMPD, or this ontology that we created as part of this project. And before we started creating the ontology, we sat down and figured out, okay, what are the design goals for this ontology? The first design goal was that the ontology should be generic, so that many industrial organizations, not just mining, not just manufacturing, can apply this procedure ontology to their data. The second design goal was that we wanted to model information currently stored in procedure documentation, and we didn't want organizations to have to create new data or conceptualize new data in order to use this ontology effectively. And this led to a lot of the design decisions that we made in this ontology, which I'll get to soon. But really, we wanted to lower the barrier to entry to using this ontology as much as possible. So we had to make many pragmatic decisions to limit the scope of the ontology to, okay, what's in this procedure documentation? And finally, the ontology needed to be able to answer specific competency questions that support maintenance technicians who use the procedure documentation, as well as engineers and schedulers who also use the documentation and are responsible for creating the documentation. So it needed to answer competency questions that help these roles with their work with the procedures. So we had to make some ontological choices, some overarching ontological choices rather. The first was which foundational ontology to use. At the time, we chose to use the ISO 15926 Part 14 ontology, which has now evolved to become the Industrial Data Ontology, because of the industrial language that it used and a growing community of interest in using this ontology in industrial spaces around this time. The second design goal was that the ontology needed to be general enough to support a range of industrial organizations, but specific enough to support users in their work. So this led to some key impacts in the ontology as to how much we wanted to axiomatize the concepts that we created. And the third goal was the scope and modularization of the ontology. So we separated the ontology into two modules, the static procedure ontology and the conditional maintenance task ontology. And I'll go through each of these modules in the next few slides. So the static procedure ontology contains information commonly found across most maintenance procedures. The reason we call it static is because we wanted to capture the data that's represented in the maintenance procedure documentation. And by its nature, this data is non-temporal. So we are modeling non-temporal procedure information here, which excludes concepts such as procedure executions. While that sort of work is valuable, we found we wanted to lower the barrier to entry for this ontology as much as possible, model the data in the procedure document, rather than modeling data that some organizations aren't really capturing yet. Regardless, there were quite a few things that we needed to model in this ontology, and this includes things like the resources that a document specifies that a procedure needs to have, the task descriptions and how they're represented, and the media used to represent those descriptions, the document itself, the ability to break down maintenance tasks or process mereology, the concept of maintainable items, hazards, and the implicit entities found within the unstructured texts in the documents. So one of the key design choices that we made when building this ontology was that we needed a way to drill down into tasks. So in procedure documentation, you often find that some tasks are represented at a very high level, for example, isolate equipment, and some procedures really break down those tasks into smaller steps. For example, this step, isolate equipment, could have multiple sub-steps, such as put up safety barrier or ensure that the pump is switched off. The Industrial Data Ontology, or ISO 15926 Part 14 at the time, had built-in mereological support for activities with a direct activity part of relationship. So for us, when using this foundational ontology, the ability to do this was very much a given. There was not too much we had to do to allow for drill down tasks or process mereology in our ontology. All we did was add two sub-properties of direct activity part of called activity part of called direct activity part of and indirect activity part of. And this enforced transitivity so that, say, resources used in one of the low-level steps would be transitively propagated up to the procedure level and could be queried at all levels of the task hierarchy. The second key design choice that we made was a consideration about whether tasks should be considered independently of the procedures that they're performed in. Now, I'm not going to go into too much detail here about choices we made here, but we decided yes, tasks should be considered independently, so that if you have a task such as isolate equipment, you want to be able to use that task in multiple different procedures and consider them the same task conceptually. There were two approaches that we considered for doing this. First is the identity approach, and second is what we call the local equivalence approach. And again, I'm not going to go into detail about what these are and their complete pros and cons. You can find them in the paper that I will link later on in these slides. However, when deciding which approach to use, we really considered, okay, the industrial organizations using this ontology, and we wanted to go with the approach that was less complex at the end of the day. So we went with the local equivalence approach. And while this approach may not be the most robust or nicest ontologically, what it did was really reduce the schematic complexity of the ontology. And for us, that was one of our goals, to lower the barrier of entry for organizations to actually use this ontology. So that's what we were looking for. The third design choice was to model epistemic versus actual activities. So to model real-world engineering artifacts in a manner that was useful for industry, we had to consider abstractions from the same perspective as the domain experts that make use of the model. So in this ontology, we modeled the ideal or epistemic activities as they are specified in the maintenance procedure document, rather than the executions. So these epistemic or specified activities are instances in the ontology. Now, in the context of ISO 15926 Part 14, there was no way to, in the same ontology, model both specified or epistemic activities and actual activities within the same context of the ontology. However, in the industrial data ontology, the decision has been made to include prescribed and actual entities as concepts in the ontology. So we now have in IDO, or the Industrial Data Ontology, a mechanism to do this, whereas in ISO 1596 Part 14 we didn't. So we didn't feel we really had a leg to stand on at that time when arguing our point about why we needed to model these epistemic or specified activities. So that just really supports and goes to show that the efforts towards IDO and the positive changes that are being made will really support the modelling of engineering artefacts such as procedures. Finally, another design choice that we made in the static procedure ontology was the choice to model implicit information in the unstructured text in procedures. So lots of valuable information about what work is performed on what equipment items is hidden right in the step texts. So in this procedure, for example, we have repaint piping valve as required. What this step tells us is that a valve, which forms part of a piping system, it needs to be repainted. How we extract this information from the procedures will come in the following piece of work that I will describe shortly. But for the ontology, we needed to include entities for modeling this information, such as an item within a maintenance process and maintenance actions. But again, I will come back to this when we talk a bit more about how we extract this information in the next body of work. In the second module, we have the conditional maintenance task ontology. So the conditional maintenance task ontology contains information typically found in inspection type procedures. So when equipment's inspected, if something is out of limits or out of range of where it should be during that inspection, then additional conditional actions need to be performed as part of the procedure. We've decided to separate this out into a second module because only specific types of procedures contain this information at all. And some organizations might not have procedures that contain this information. So it was really important for us that we separated this out into a separate module as to not complicate the original static procedure ontology and to lower the barrier to entry for using that ontology. One of the key design choices that we made in building the conditional maintenance task ontology was to align the concepts in the ontology with an existing piece of work on failure modes and effects analysis. So we can see we've reused concepts such as failure event, functional failure, and failure mode observation. And in the future, we hope to perform some more work to figure out how these ontologies can be joined together and what is the value of maintaining visibility over, for example, our failure mode observations throughout the maintenance work management process. Feel free to pause the video here and have a look at some of these links. Now, this is where we put all our resources for this ontology, so you can get started with this ontology. We have a GitHub repository and a fully implemented test suite for the ontology written in Python. We also have documentation, and this ontology is available on Onto Commons and has been provided a fair score and is ready to use. Now, having implemented an ontology for maintenance procedure documentation, we now want to use the ontology in a semantic quality assurance use case. We wanted to show the value of this ontology for industrial organizations, which is why we embarked on this second piece of work. For this, we created the Quokka workflow. So the Quokka workflow uses existing tools from the Semantic web stack, as well as OpenAI's OpenAI's GPT 3.5 model to take data from a CSV format into an OWL ontology that can be validated for consistency and correctness in a way that is generic. So we've developed some Python code that is completely configurable. So you can come in with a new language model new set of templates and new set of SHACL shapes, and this code will work to perform this semantic validation process. So in our process, we start with a set of CSV files containing data from the procedure documentation. In the first module, the completion module, we aim to make implicit data in the procedure documentation explicit by extracting entities from the unstructured text in that documentation. And then we transform the documentation into a set of CSV files that is suitable for the second module, which is the consistency module. In the consistency module, we extract data from CSV format into an OR-based ontology, so we can check it using our reasoners. And then in the final module, the correctness module, we perform closed world constraint checking using SHACL on the ontology to check the data for correctness. And I'll go through each of these modules in more detail now. For this work, we use iFixit maintenance procedures. Because we were using a proprietary large language model in this work, we didn't have permission from a company to use their procedure data for this work. So instead, we used this publicly available data set available under a Creative Commons license, which is emblematic of the procedures that we see in industry and the language in the procedures that we see in industry. So we're able to test this workflow using procedures that were very representative of the ones that we see in the organizations that we work with. The first module in this Quokka pipeline, or this semantic quality assurance pipeline, is the completion module. So the completion module makes implicit information in the procedure documentation explicit for mapping to an ontology. And this process involves, first, extracting information from the unstructured text in the procedures. So this procedure has a step, lift up the plastic cover, and we can extract these entities using a large language model, OpenAI's GPT 3.5 model. I'll show how that's done in the next slide. But we can extract entities such as lift up being an activity, item being a plastic cover, and we can say that this activity has patient or has participant plastic cover. The schema that we used is based off the Menti schema, which is a schema created by the UWA NLP-TLP group. So we've reused some of that work here. Then, once entities have been extracted and relations have been extracted between those entities, we map the data that's extracted, as well as the structured data from the procedure, to an expected output structure according to some configuration file. So this workflow is entirely configurable. So by respecifying the configuration file, you can change the expected output of this completion module. To perform named entity recognition and relation extraction with OpenAI, we did what's called a few-shot learning approach. So few-shot learning is providing an LLM or a large language model with a few examples, with an instruction and a few examples of how to complete that task effectively. And by doing that, we can create a named entity recognition model or a relation extraction model with low effort and without using a very expensive to create annotated data set. So in this prompt, which we give to the large language model, we first establish a role. We say, okay, you're a named entity recognition assistant. We establish a schema. We say, these are the things that you can, these are the concepts that you can use to tag this text. We include something to limit hallucinations. Say, if you don't know what to say, then don't say anything. We then give a few examples of expected inputs and outputs, and then you set up a response and provide it with a text. So doing this, we can essentially replicate a named entity recognition model, like the models we've been using in natural language processing for quite some time. So the output CSVs from the completion module perform the input to the consistency module, which is the next module. So these CSVs are structured according to a configuration file, and they contain, for example, prefixes for entities. So because we are about to transform this data to an OWL ontology, entities need to have prefixes or something to say what namespace or what IRI this entity is going to have. It contains the implicit information from the procedure step text that have been extracted in this module. So for example, we have lift up and plastic cover. And it also contains the structured information from the document, such as the steps themselves, the tools and resources required for performing the procedure, etc. In the next module, the consistency module, we take this CSV data and then we transform it into an OWL ontology. And to do this, we use the Otter framework. So Otter has been created by the Sirius Center, and the idea of it is to create ontologies using templates. These templates allow us to take these CSV files, transform the data into the Otter language, and then output an OWL-based ontology. Once the ontology has been transformed into an OWL format, we can use OWL reasoners such as Pellet and Hermit. In this case, we used Pellet to check the data for consistency against the axioms of the ontology for maintenance procedure documentation. So for example, in the OMPD ontology, we decided to model tasks sequentially and enforced a sequential structure for the steps in the procedure. The reason that we did this is described in the paper. I won't go into that here. But rather, in this module, we can check if the data populated in the completion module and the consistency module is consistent with this axiom. And so if there are branching task sequences or procedures that don't contain a linear structure, then that's not consistent with the OMPD ontology and a reasoning error will be thrown. Once the ontology is consistent, we can then run the correctness module. In the correctness module, we use SHACL shapes to perform closed world reasoning and constraint checking on the ontology. An example checks include orphan tasks, so tasks that don't have a procedure process as a parent, tools with no action, so if you have the completion module identifying a spanner is a tool, that spanner then needs to be related to an activity that that tool is used for. And unknown activities, so we can use SHACL to check terms against some standardized list of accepted terms. All right, so we've now shown the ontology for maintenance procedure documentation, and we've also shown a semantic quality assurance pipeline for this documentation as a demonstration of how this ontology can be used in practice. But what does this mean for the industrial data ontology community? So the ontology itself is a use case that's in support of the industrial data ontology effort. While there's not a formal IDO use case at this time, we have some interest in formalizing it if the need arises. The second benefit is that OMPD balances rigorous ontological modeling with user-centered ontology design. So we really considered the end users of this data and what their needs were when designing the concepts in this ontology. So this led to key design choices such as how to simplify the schematic complexity and how many axioms we really need in the ontology. So this is a really pragmatic example of how to develop an ontology for industry to lower the barrier to entry for using this ontology in an industrial space. And finally, OMPD supports IDEO's decision to include prescribed and actual entities in the ontology, which is what I spoke about briefly when we were modeling our epistemic versus actual activities. The Quokka workflow, or the semantic quality assurance workflow, is an early example of using large language models and ontology together as a basis for future discussion in the IDEO community. Quokka is a published example of the use of semantic web tools in the industrial data ontology community, namely OTTR templates and SHACL shapes. And finally, Quokka is configurable with open source as a Python implementation so that anyone wishing to turn text-based documentation into a validated ontology can use the code to accelerate their work. This work is published in 2 places. First, we have our ontology for maintenance procedure documentation paper, and we also have that ontology being used in our semantic quality assurance use case paper, and they can be found at these QR codes. Thank you very much for listening to this presentation. Please reach me if you have any questions.